What's up, you cool cats? Today we're going to talk about graph transformations. This is one of my favorite lectures in the unit, in the whole class even, because it's going to let us see how the geometry and algebra of graphs go together piece by piece. We're going to be able to dissect formulas and understand how they work. The goal of a graph transformation is to start with a toolkit function. Let's say here's y equals x squared. We can start with this, and graph transformations are a tool to turn it into any other parabola we might want. So graph transformations do things like move the parabola left or right or up or down. So we could move it left, like so. And then maybe we could move it down. We could flip it over. And maybe we could stretch it or shrink it as well. But the point is that graph transformations let you piece by piece understand what you need to do to the equation of the graph to affect each of these changes on the graph. So starting with the toolkit parabola, you can graph any other quadratic function. They're also good for if you know a graph, if you see a graph and you recognize that it's related to a toolkit function, you can usually write down the equation from looking at the graph. So they go both ways. The most important thing is it's another way to explore the symmetry between the geometry of equations and their algebra. So what we're going to do today is explore 6 transformations, and that's all we'll need to do everything. We'll explore those 6 transformations bit by bit, one by one. Let's get started. Probably the easiest transformation is the vertical shift. And this is what's going to move your graph up and down. So if I want to do a vertical shift, think back to the previous lecture, 3.4. I had that semicircle that I was able to move up 6 units by adding it to the function 6. So if my original function, let's say, is f of x equals x squared, so there's that parabola again. X is the input, and x squared is the output. We're going to think a lot today about inputs and outputs. So remember, f of x, this whole thing, describes the output, and x right here is your input. So the output is the y-coordinate, and the input is the x-coordinate, right? You put x in, you get y back, and that's how you graph it. You'll graph this point, x, y. So the y-coordinate tells you how far up or down you go. The x-coordinate tells you how far left or right you go. If I want to move this thing up, I should make the y-coordinate bigger. So this whole equation, this whole right-hand side here refers to y. When x is 2, y is x squared is 4. When x is 10, y is x squared, which is 100. So if I want to move this whole thing up, I need to make y bigger. So let's say I change that to a new function, and let's call it, how about h of x? It's going to be the same function, but I'll add 3 to it. So I've added 3 to the output. So first you find x squared, and that gets you this point, and then you add 3. And that's going to make the y-coordinate 3 bigger. So for example, over on this graph on the left, I have points like, let's get rid of it. Let me draw a new graph. Here's f. So over on the graph of f, I have points like 2, 4, and 5, 25, right? So over here on the right, if I plug 5 into h, I'll just do this once. H of 5 is, well, it's x squared plus 3, but it's the same as f of 5 plus 3, because h of x is x squared, and f of x is x squared plus 3, and f of x is x squared. So I'm taking the value I would have gotten out of f, that's x squared, and I'm adding 3 to it. So instead of h of 5 being 25, h of 5, actually, I'm going to take this graph here. H of 5 is going to be, let me draw this in green here. H of 5 is going to be 28. And for h of 2, it's 2 squared plus 3. That's the same as f of 2 plus 3. So instead of getting a 4 out, I'm going to get a 7 out. So this is the point to 7. And that's the same no matter which point on f we started with. If I plugged -3 into f, I'd get a 9 out. So here's -3, 9. If I plug -3 into h, I have to get a 12 out because it's whatever f gave you, but 3 bigger. So every single point on this graph does the same thing. They all do it individually. This is a point-wise operation, but every single one of them moves up 3 units. So the visual effect is, looks like the whole graph has moved up 3 units. So this is the graph of h. It's just the same graph, but shifted up 3 units. So h of 2 is 7 because f of 2 is 4. It's like this point has moved up. Since every point moves in the same direction in the same distance, the whole graph moves up. If I wanted to go the other direction, I could say maybe g of x equals x squared, or here, let me write it this way. I'll take f of x and subtract 4. I'll make the output smaller. So I could say that g of x is x squared minus 4. Okay. So f of 2 is 4, but if I plug 2 into g, I'm going to take that 4 and subtract 4. So g of 2 will be 0. Minus 4, it's like it moved the point down 4 units. And g of 5 will be 21, and g of -3 will be 5, because it's whatever you got out of f, but then 4 is subtracted from that output. So there's the graph of g. So that's how you do a vertical shift. You take your old equation, and you add a number to go up, you subtract a number to go down. Well, next thing I want to do is, if I can move it up or down, that's good. If I can move it left or right, that's even better. So in the vertical shift, I looked at my output, and I wanted to, sorry, one moment. I got my output, and I wanted to add a number to the output to make it bigger, or subtract a number from the output to make it smaller. So now in a horizontal shift, I'll be doing the same thing but with the input. So let's say f of x was equal to the square root of x. So I'm going to use a new function each time. Let's say f of x was equal to the square root of x. And instead of changing the output, if I said square root of x plus 5, that would move the whole graph up 5 units. But I don't want to go left or right this time. I want to go, or I don't want to go up or down 5 this time. I'm sorry. I don't want to go up or down this time. That's what that would do. I want to go left or right. So what I'm going to do is change the input instead. What if I say, here's my input, but I'm going to change that. I'm going to change it to g of x equals f of x plus 5. So I'm going to plug x plus 5 in instead of f, or instead of x. So g of x is going to be the square root of x plus 5. So that's going to move the graph horizontally instead of vertically. Now, how it moves it is a little bit tricky. Let's take a close look. This is one where your intuition will mislead you, so I want to do this next part carefully. Here's the graph of f of x. This is what the square root function looks like. This is from your toolkits. And it's got points like the square root of 1 is 1, square root of 2 is 4, the square root... Oh, I did it again. Sorry. I do this every year. I do this same mistake. The square root of 4 is 2, the square root of 9 is 3, and so on. There we go. Every year I do that. I don't know why. So g of x is the square root of x plus 5. So what happens if I take g of 9? Or what happens if I take g of 4? Let's take g of 4 here. So when I plugged 4 into f, I got 2. But when I plug 4 into g, something else happens. G of 4 is the same as f of 4 plus 5. So it's the same as f of 9. G of 4 is the square root of 4 plus 5, which is the square root of 9, which is 3. So g of 4 is 3. So don't think of this as an up or down move, though, because remember I changed the input. Think of this as a left or right move. G of 4 is 3 because f of 9 is 3. When I plug 9 into f, I'd get 3. Well, when I plug 4 into g, 4 goes into g, but f only sees x plus 5. F sees a 9, so the input to f is 9. We're changing the input before it gets to f. So g of 4 is equal to 3 because f of 9 is equal to 3. So it's like this point has moved to here. Adding 5 has moved us left. If I did g of negative 1, that would be the same as f of negative 1 plus 5, which is f of 4. We know that f of 4 is 2, so g of negative 1 also has to be 2. G of negative 1 is the same as f of 4. It's the same output. So what this plus 5 is doing is saying, you can give me an input that's 5 smaller and still get the same output. So this is the point, negative 1, 2. So if I want an output of 1 from g, what input should I give? G of what is equal to 1? Yeah, it'll be negative 4. G of negative 4, if I give a negative 4 to g, f's not going to see it until it's turned into a 1, because g of negative 4 equals f of negative 4 plus 5, which is f of 1. So I can give it a number 4 smaller and still get the same answer. So g of negative 4 is the same as f of 1, so that means that point is over here. This is negative 4, 1. So this entire graph has moved 5 units to the left. So adding moves to the left. That's where your intuition is going to deceive you. It feels like adding should move to the right, but it's not actually how it works. Think of this as a $5 discount, right? Because f of 36 equals 6. The square root of 36 is 6. Think of it like, I have to pay $36 to get a 6 out of f. But if I want a 6 out of g, I've got this $5 discount. It's like a coupon for $5 off, right? We're adding $5 to our purchasing power. So g of 31 is 6. I only have to pay $31 for the same 6, because 5 gets added to it before f sees it. So the input for g can be 5 less than the input I would need for f. That's what this 5 is doing, is saying, you can give me an input that's 5 less. So what if I do want to go to the right? Well, let me draw h here. If I do square root of x minus, let's do minus 2. This is like saying, oh, you have to pay me $2 more. So f of 9 is 3, but if I take h of 9, I'm going to get the square root of 7, and that's no good. But if I take h of 11, that's the same as f of 11 minus 2. So that's the same as f of 9. So this minus 2 is saying you have to pay $2 more. So h of 11 is the same as f of 9. It's 3. And h of 6 is the same as f of 4. H of 3 is the same as f of 1. So h moves your whole graph to the right. So don't be deceived. If you want to move to the right, you do f of x minus b, and that moves you b units to the right. So the horizontal shift, it feels like it's backwards. It feels like adding should move you to the right, but in fact you want to subtract. Whereas vertically, this would move you a units up. So now we've got our vertical shifts and our horizontal shifts, and we can even put these together. Let's say I have the graph of an absolute value function, and that's got the point 0, 0. So this is y equals the absolute value of x. And let's say I would like to have a graph that's like an absolute value function, but instead the vertex is over here at 5, 2. So it's the same V shape, but now it's up here. So the way we can think of this is to get there, we had to move to the right 5 units and up 2 units. So I should do a horizontal shift 5 to the right, and I should do a vertical shift 2 up. So my new formula is going to be y equals, well, let's see. If we go up by 2, it'll be the absolute value of x, and then on the outside, plus 2. But that's not quite all we need. I also need to go 5 to the right. And the way I do that is by subtracting 5 from the input. So if I subtract 5 from the input and add 2 to the output, that'll move me 5 to the right. It's like that $5 discount. And then 2 up, we get an extra 2. So for example, let's make sure that this is the right formula. If I plug in a 5, it's going to be 5 minus 5 in here. That's 0 plus 2. So what if I plug in, how about a 7? The absolute value of 7 minus 5 plus 2. Well, that's the absolute value of 2 plus 2, which is 4. So here's the point 4, and that really is on the graph. So it's like the point 0, 0 moved up to 5, 2, and it's like the point 2, 2 moved up to 7, 4. So we're doing 2 transformations at a time. So now you start with one of your toolkit functions. If you want it to start somewhere other than the origin, you can do that. That's what shifts are for. I'm going to pause the video here, and we'll come right back and do flips next.